We are going to start linear vector spaces, and linear vector spaces are very, very important in quantum mechanics. Now, before going to begin linear vector spaces, let's learn about vectors in general, or uh, vectors in n dimension. So, what is a vector in n dimensions? An n-dimensional vector is given by this expression, where x, capital X, is a vector, small x1 and x2 up to xn. These are the components of this n-dimensional vector. E1 is a unit vector, E2 is another unit vector, and till En is the nth unit vector. So here these E's are unit vectors, and this x1, x2 up to xn, these are the real numbers. Just like in two dimensions, we have x, y. So x and y are real numbers, and for that case, E1 is I unit vector and E2 is J unit vector. Similarly, in three dimension, we have X, Y, and Z. And in that case, E1 is I unit vector, E2 is J unit vector, and E3 is K unit vector. But as we are extending this idea to n dimensions, so an n dimensional vector is represented by this capital letter. It can be X, Y, Z, U, anything. And then there are components, and those components are n. There are n components. For example, in this shorthand notation, uh, I is running from 1 till n, and xi is the ith component of the n-dimensional vector, and ei is the ith unit vector for that nth dimension vector. So an n-dimensional vector is given by this expression, and this is a generalization of our two and three dimension vectors. Now remember, two-dimensional vectors can be drawn on the plane, and three-dimensional vectors can be shown in the usual 3D space. But you cannot show an n-dimensional vector geometrically. This is just an abstract idea, and this is really helpful in quantum mechanics. So you have to learn the subject, you have to learn these n-dimensional vector in the spirit that these will be extensively used in quantum mechanics. Now we are going to define some terminology about n-dimensional vector, and the first one of that is n-tuple. So an n-tuple is a sequence of n real numbers, like this one shown here. This x1, x2, and up till xn. These are the components of our n-dimensional vector, and this bracket representation, or this is the point representation of an n dimensional point. So this bracket shows a point in n dimension. Remember, you cannot show this physically, but this is an abstraction. This is an abstract idea, but this is really helpful. So an n tuple is a sequence of n real numbers. Just like in two and three dimension, the we have xy in a bracket form, or the point form is the ordered pair xy. So, and in three dimension we have xyz. But as I mentioned, that we are extending the idea to n dimension, so xyz and those letters will not be enough for n dimensional vector. So that's why we are switching to this subscript notation, where the components will be represented by x subscript 1, x subscript 2, and so on. So xn is the nth component of that n-dimensional vector. So this thing is called as the n tuple. Then n space. What is an n space? Our n space is represented by Rn, where R stands for real and n stands for n dimensions. So what is an n space? N space is the set of all ordered n tuples. If you make a collection of all n tuples, then that set is called as n space. Uh, uh, let me just quickly remind you that what's a set. A set is a collection of well-defined different objects. So if you make a set of all n tuples, remember that every one will be included. uh, all possible n tuples will be included in this set. So then this set is called as an n space. And remember, it has nothing to do with this usual 3D space or 2D plane. This is just a name to represent the collection of these ordered n tuples. So these two definitions are very important: n space and n tuples. N tuple is this point form of the n unit vector, the n dimensional vector, and n space is the collection of all ordered n tuples, a whole set. You have to include every possible n tuple in this set, and this whole set is then called an n space. And then later in our lectures, we will study about vector spaces. This is simply just space, but we will discuss vector spaces. So vector space has some axioms to obey, and we will discuss that. But at the moment, we are only concerned with n-dimensional vectors and some operations on n-dimensional vectors. Then here are some important notes about these n-tuples. An n-tuple can be viewed as a vector, just like you have in two dimension. Uh, in an xy plane, you represent xy pair as just a point in the plane. It can be in the first quadrant, the second, and the third, or in the whole plane. But when you connect that point in two dimension to the origin, and you put an arrow at the end of that point, then you get a vector. So that thing can be extended to n tuples as well. For example, if this is an n tuple with n components, this is in the that n tuple, or this is the vector in the n tuple notation. So when you connect this n tuple with the origin, and remember the origin in n dimensional will be having all components equal to 0, and that's called the origin of the n-dimensional space. So when you connect this point, this nth, this n-dimensional point with the origin, you will get an n-dimensional vector, and that is, as I mentioned, that cannot be shown on a plane or in 3D space as a line or something like that. But this extension is helpful, that you can weave this n tuple as a vector when you connect this with the origin. Similarly, an n-dimensional vector, you suppose you have an n-dimensional vector u1 with components u1 u2 up till un, and this is a part of the n space, or this vector belongs to n space. Now this is one representation. Look at, we can use these brackets, we can use uh, these curly brackets, or these big braces. So this is one notation of representing an n tuple or an n-dimensional vector. But this n-dimensional vector can be represented with a column vector or a column matrix, and this idea is very important for quantum mechanics, where we'll be using uh, column vectors for n-dimensional vectors. So in this notation, the usual two-dimensional vector will be just a column of x and y, and the usual three-dimensional vector will be a column of x, y, and z. So the point is that we can represent an n-dimensional vector with a column, with a column matrix. This is also called a column vector. So let's proceed towards special examples. Uh, as this is the representation of n space, where r stands for real number and n is the dimension. So let's see special cases. If n is equal to 1, then we are in R1, R1 space. R1 space is just one dimensional real line, and this one space is the set of all real numbers. If you have a set which includes all real numbers, so then that set is called one space. And this is just the name, and geometrically this is just a straight line, a horizontal straight line, where every real number lie on that line. So this set of all real numbers is called one space. Then if n is equal to 2, then we are in R2 space, and R2 space is the set of all ordered pairs. And now, in our general notation, we will represent ordered pairs with x1 and x2 components, not with x, y, which was our usual notation for two-dimensional vectors. And this is the geometrical representation. This is an ordered pair where this is the first component, or if this is my x-axis, x1 axis, and this is my y1 axis. So this point is x1, x2. And in your usual notation, this was earlier, it was x and y. Now, if I connect this x1, x2 point with this origin, and this origin is 0, 0, so I will get this straight line, and this is the vector form now. So this is a vector, and this is just a point representation. So our two space, or the usual two-dimensional space, is a set of all ordered pairs. This thing is important, set and having all ordered pairs. So that collection of all two-dimensional tuples, or 2D vectors, is called as a two space, or a two-dimensional space. Then if n is equal to 3, we have R3, and this is called the three space, or the usual three-dimensional space. And the three-dimensional space is a set of all ordered triples. with this notation. Earlier this was x, this was y, and this was z, and now for this general representation, this is x1, this is x2, and this is xn. So this is our usual three-dimensional space, and this three-dimensional space is a set of all ordered triples. It will contain all of them. Every possible uh, ordered triple must be included in this set, and then this set is the 3D space. Then n is equal to 4. N is equal to 4 is called the 4 space. Now this 4 space idea is useful in special relativity, where you represent uh, different quantities with 4 vectors. uh, every vector has 4 components, and the set of all those ordered quadruples. Now here this is called as ordered quadruple, and this can also be represented as a column matrix. So this idea is very helpful in special relativity, where things are termed as 4 vectors, and this is just one example for from that special relativity. Um, the set of all these ordered tuples in special relativity form a four-dimensional space, and that four-dimensional space is known as a Minkowski space-time, or just Minkowski space. And in that space, we have four-dimensional vector. So now look at this is a four-dimensional vector in the column representation: x0, x1, x2, and x3. This is um, and look at our notation. Our notation is x1, x2, x3, and x4. But in special relativity, they start with x0, and this x0 is usually given by ct, and c is the speed of light and t is time. So this is ct, and this x1, x2, and x3, these are the usual space coordinates. So this column vector is called as a 4 vector. And this thing is this matrix, this 4 by 4 matrix is a transformation. Remember, in our basic linear algebra, you studied matrices, and matrices are called as transformation. And in this case, in the case of special relativity, this transformation is called a Lorentz transformation. And a Lorentz transformation converts a vector, a 4 vector, from one inertial frame to another inertial frame. So look at this is also a four-dimensional vector with head on top of it, or with bars on top of it. So if this is our rest frame, these are the coordinates in the rest frame, then these will be the coordinates in the moving frame. And uh, who is doing this job? Who is doing this conversion? So the Lorentz transformation is doing this conversion from one frame of reference to the other frame of reference. So all of the special relativity is about four-dimensional spaces, which is, as I said, okay, that's a Minkowski space, and the calculations are done with the help of the linear algebra, and our linear vector spaces are simply this four-dimensional space. So this is the n is equal to 4 case. Then we can go for n is equal to 5, n is equal to 6, and so on. But n is equal to 6 case is important for physicists. So let's switch to n is equal to 6. Now, when n is equal to 6, we will have our 6 space, and our n tuple will have then 6 components: x1, x2, x3, x4, x5, and n6. And the collection of all um, uh, mm, those points in the six-dimensional space, that collection will be called as a six space. And this six space is usually known as phase space in classical and statistical mechanics. And in phase space, we do calculation, or in phase space, we have three position coordinates and three momentum coordinates. So that collectively make up six coordinates. And usually motion is described, or the dynamics of the system are described in a phase space, where we have three spatial coordinates and three momentum coordinates. So this is very important for that classical and statistical mechanics, and occasionally in quantum mechanics. So the idea is a phase space is usually in 6 dimensions. Then we can extend the idea. We can go to n is equal to any number, but let me just mention here, just an introduction, that Hilbert space in quantum mechanics is in general an infinite dimensional space, where you have a collection of vectors, or state functions, or state vectors, or whatever you may call that. And those collection, they also form a space, and the name of that space is a Hilbert space. It is actually an inner product space. We will discuss Hilbert space later in this linear vector spaces course, linear vector spaces discussion. So this is uh, just remember the name at the moment. We'll learn about Hilbert spaces later when we develop our terminology of linear algebra. Uh, Now operations on vectors in Rn. You have learned or you know how to do different operations on vectors in two and three dimension, like how to add vectors, how to subtract vectors, how to multiply a vector with a scalar, how to multiply vectors with each other, the dot and the cross product. All those are operations on vectors. So you know how to do those operations in two and three dimension. Now how to do those operations in n dimension, or how to study those operations. So for this purpose, consider two vectors. Suppose we have two n-dimensional vectors. One vector is u. Remember, vectors are represented by bold letters. This is capital U, and the components of are real numbers, and they are represented by just unbold letters like these u1 u2 up to un. These are the components of the u vector. Similarly, we have another vector which is represented as bold, and these are the components of that second vector, v1 v2 up till vn. So we have these two vectors, and let's study different operations, very simple operations on these basic operations on these two vectors. First, this is not an operation, this is just a definition. Equality of two vectors, when two vectors will be equal. Suppose this is u and this is v. So if u is equal to v, this will be possible if and only if they are if every component is equal to its corresponding component. For example, if two vectors are equal, then this first component of this vector will be equal to the first component of the second vector. The first component of this u vector will be equal to the first component of the v vector, and similarly the first component of the u vector will be equal to the nth component of the u vector will be equal to the nth component of the v vector. So only then these two vectors will be equal, if they are equal term by term, component by component. The corresponding components must be matching, and then the vectors will be equal. Then addition of vectors, this is very important for vector spaces. This operation is extremely important for vector spaces. So suppose we are adding these two vectors u and v. So the addition is very simple. This is just an extension of the usual idea in two and three dimensional space, that when you are adding vectors, add the corresponding components. By that I mean that add u1 with v1, u2 with v2, and un with vn. Now this vector addition is very simple when we write our vectors in column notation, as as we discussed here, that an n-dimensional vector as this one, an n-dimensional vector can be represented by a column vector. So if you represent your vector with a column, then operation with those vectors become very simple. And you can see here we are adding these two vector u and v, and this is the same thing. This thing, this is the n tuple representation, and these are the column vector representation. So if this is my first vector with components u1 u2 till un, and this is my second vector with components v1 v2 till vn, and I'm going to add these two vectors. So this is like just adding this is like adding two column vectors. So these, add this with this, and u2 with v2 until we end with un with vn. So this is the resultant vector. This is u plus v vector. And similarly, you can do subtraction. Just put a minus sign here, and then uh, here a minus sign will appear. So that's the same thing. Then the difference, as I discussed, difference can be shown here. Just put a minus sign here, and everywhere a minus sign will pop in here. So this will be the negative of the difference of the two vectors. Then scalar multiplication. As vector addition is important, scalar multiplication is also another important idea, and this idea is important again for defining a linear vector space. So you have to fully focus on these two definitions, that how to add n-dimensional vectors and how to multiply a scalar with an n tuple, or how to multiply a scalar with a vector. So suppose we have this u vector again, this one, and I'm multiplying this vector with a constant c. Now remember, this c is a real number. This is not a vector, this is just a constant number, but this is a real number. So multiplication of this real number with this vector is given by just multiply every component with the c. Like this u vector has these components. These are the components of the u vector. So if you want to find cu, you have to multiply c with every vector, with every component, sorry. So c is multiplied with the first component, c is multiplied with the second component, until this the same c is multiplied with the nth component. So this operation is called as a scalar multiplication, and this same thing can be shown in the matrix form, where u is a vector, the same this vector, and we are multiplying this with a scalar alpha. This scalar can be represented by c, alpha, k, or whatever you like. So here in this matrix form, I'm multiplying this uh, n-dimensional vector with a constant alpha. So this is a matrix, and this is just a constant multiplying this matrix. So this constant will be multiplied with every component, and now this is my alpha u. This is the new vector is alpha u, where the components are multiplied with this scalar number. And as you know from your usual 2D and 3D spaces, multiplying a vector with a scalar does not change its direction. The vector stays in the same direction, but its magnitude is either magnified or diminished. So either its magnitude or its norm will increase or it will decrease depending upon the value of the c. If the c is larger than 1, then it will magnify your vector, or it will increase the magnitude. If the c is smaller than 1, then it can diminish, or it can reduce your vector in size. So this is scalar multiplication. Then we have this is just a terminology. Now we have a zero vector. The representation of a zero vector is this capital zero, and the n tuple representation is that every component of the zero vector will be zero. So a zero vector in three dimensional will be equal to just an order triple with three zeros, and a zero vector in two dimensional will be an ordered pair with just two zeros. So this zero vector is usually the origin um, of your space, whether it's a n-dimensional space or a 2D or a 3D space. So this zero vector is the origin of the space, and this zero vector is given this fancy name of additive identity. This is also known as additive identity. So the additive identity in Rn is this n tuple having every entity as zero. Then we have a negative of a vector, where the negative of a vector is just multiply uh, every component of your vector with -1. So the negative of a vector is just the reverse of your vector. If your vector is pointing leftward, then and if you multiply this with -1, then it will now be pointed in the rightward direction. So negative of a vector is just a scalar multiplication with -1. And again, this negative of this vector is also given this fancy name of additive inverse. So if u is your vector with these components u1, u2 till un, then minus u will be this vector, minus u1, minus u2, minus u3 till minus un. And this minus u is the additive inverse of this original u vector. And if you add u with minus u, you will get zero vector. So this idea of zero vector is very important, and you need this zero vector. And remember again our notation, this side is written bold, and these components of the n tuple, these zeros are written, these are not bold. So vectors are represented by bold face letters, and the components are just unbold letters. So mm, these things will be helpful in the definition of the linear vector space. Uh, Vector addition, very important, scalar multiplication, yet another important operation. And then these two definition are these two special cases, special vectors like additive identity and additive inverse. These four will be used in our definition of the linear vector spaces in our coming lectures. So these are simple operations on vector, and you can do some complicated operations like taking dot product and cross product and so on. Everything can be you can do for these n-dimensional vector, and we will study those, especially the dot product. The dot product is in n dimension. Usually it's called the inner product, and we will discuss those operations later. But at the moment, these operations will be helpful in the definition of the linear vector spaces. So um, I just introduced them for the n-dimensional vectors, but you already know all of these operations for 2 and 3 dimensional. So just extend that idea of those operations. Now here is a quick quiz. to just check your knowledge of these previous operations. For example, you have these two vectors, and these are three-dimensional vectors, and they belong to R3, and you are asked to find each of these. So first, you are asked to find u plus v. Now, u plus v is very simple. Just add the corresponding components of different vectors. u1 plus v1, u2 plus v2, u3 plus v3, and so on. So this is a three-dimensional vector. This is also a three-dimensional vectors. So add these, mm, add them component by component. So minus 1 will be added with 2, 0 will be added with minus 1, and 1 will be added with 5. So you will get this u plus v vector. Or you can do the same thing in matrix form. Write this as a column matrix and write this as a column matrix, and then add those two columns. So you will get this resultant vector u plus v. And you can just name this, like you can call this w. Then the second operation is also simple. Find 2u. 2u mean multiply this vector with just 2. So multiplying this vector mean with the scalar 2 mean I have to multiply every component with 2. So if I multiply this u vector with 2, the first component will become minus 2, the second will remain as it is, because 2 into 0 is 0, and when I multiply this with 2, it will become 2. So then 2u vector will be minus 2, 0, and 2. And then you can do this other operation, like v minus 2u. Now this is your v vector, and you found 2u here. So now you do a subtraction, you find the difference. So just do it. Then uh, another quick quiz is that we have now three vectors, and those three vectors are not three-dimensional vectors. They are now in four dimension. So these are four-dimensional vectors, and we have to perform the following operations. Excuse me. The first operation is that find a new vector x, which is 2u minus v plus 3w. So we know only u, v, and w, but we have learned about these operations: scalar multiplication and vector addition. So now um, this x has the combined effect of this has combined operations. This expression, what are those combined operation? It has scalar multiplication, and it has a vector addition. So we have to do addition and scalar multiplication collectively. So you have to find first 2u. 2u is very simple. Just multiply this first vector with 2. Then v will be used as it is, and you have to find 3w. So for 3w, you have to multiply this um ordered quadruple with 3. So every component will be multiplied with 3. This will become minus 18. If I multiply this with 3, this will become 3 twos are 6. This will stay 0, and this will become 9. 3 into 3 is 9. So then you will put all these things here, and then you will add and subtract accordingly, according to these signs. So you will get the new vector x. Then once you get this new vector x, then you can do some further operations. Take this new vector x and add this with the w vector, and then multiply that whole combined vector with this 3 number, and then verify that this side is equal to this other side, where the first vector u is multiplied with 2, and we have then subtracted minus v, and then we have added this, you have to add then this x again. So mm, just take a pen and a page and verify or perform these operations, just as a quick quiz. So this is it for the day, and let me quickly summarize that what we discussed in this introductory lecture. We introduced n-dimensional vectors, and we represented those n-dimensional vectors with n tuples, and n tuples are simply this n tuple is simply this sequence of real numbers. Then we defined the n space. Okay, it is a collection of all ordered n tuples. And then we discussed okay, vectors can be represented with column matrices. And this idea is very, very important, that if you represent vectors with column matrices, then operations with those column matrices become very easy. If you have already if you are already familiar with matrix addition, multiplication, and so on, so then this doing algebra or doing operations on vector in the matrix form is usually very simple. Then we discussed some special cases for these different spaces, and finally we learned about different operations on these vectors. So these operations will be very very helpful in our upcoming lectures of linear vector spaces. Thank you.